Hey, what's up? It's Tricky. I use Ctrl-Z all the time. I use it when designing circuits. Oh no. Or CAD modeling. Oh no. Or editing this video. Oh no. Unfortunately, in the real world, you're stuck with your mistakes.
This took me like 2 hours. Oh no.
But I think I can solve this. And what started as a simple idea turned into a 6-part engineering mess. Before building my own machine, I want to explore what kinds of technologies already exist. Leo put together this 2-axis Cartesian robot like the kind used in CNC mills. It works kind of like a 3D printer. The end effector can be moved along the X and Y axes independently, allowing us to reach any point on the plane. It works with these stepper motors. This pulley has teeth that mesh with the teeth of this timing belt, so as the motor rotates, it pulls itself along this axis. So if we attach a pen, it can draw a straight horizontal line. If we instead activate the other axis, we get a vertical line. And we can program these to activate however we want. So by alternately activating the axes, we can draw different shapes. And by cleverly programming the axes, this can draw any form we want. This clearly has a lot of relevant functionality, so what's missing? When the motors are active, even if they're not moving, they're locked, so I can't move the end effector. And even when I disable the motors, I can't meaningfully draw with this. It just really wants to move in straight lines. Trying to draw curves or angles is a non-starter. This is my honest best attempt at drawing these basic shapes. And it's clearly not working. So I'm gonna steal inspiration from the precise stepper motors, but otherwise we're gonna have to come at this with a different approach. Let's take a look at another mechanism called a scissor linkage. You've seen these on scissor lifts, car jacks, and on, cartoon boxing gloves. I'm thinking this linkage can form the main arm of our robot. You can see we get a lot of extension for the arm with this mechanism. It's especially advantageous for us since this mechanism converts rotational motion into linear motion, so we can control the extension with those highly accurate stepper motors. The next mechanism I need is gears to transfer rotational motion. But before I explain this, it's probably a good time to actually talk about the design for this project. In order for our device to be able to reach any position, the arm needs to be able to extend but also rotate. For this we need another mechanism. We'll be using gears to transfer rotational motion from one motor to another. We also need to know the position of the motors. For that, we can add potentiometers in line with the motor shaft. These are devices that increase their electrical resistance when they rotate, so we can measure their resistance and that'll tell us their position. I'll assemble this motor on the right first. I'll go ahead and attach the first potentiometer to the frame. I can then link that to the motor shaft with this coupler. Different parts arrived at different times for this build, so here for example I have a 3D printed placeholder. You see when the motor shaft rotates, so does the potentiometer. Yay! Next I'll attach this interface to the bottom of the motor, and I can use the existing mounting holes. You can see this new base just has a little nub sticking out of it. This will fit into a bearing so that this whole motor assembly can rotate freely. We can see it does indeed rotate well, but it's very wobbly, and that's no good. I'll jump up to a much larger bearing so there's a nice wide base. And the result is great. It still spins freely, but now is very secure. Let's now turn to the other motor. Remember, its job is to force the entire other motor assembly to rotate. It'll do that with this gear segment. Rotating the shaft of the first motor is having the desired effect. We transfer its rotational motion directly onto the second motor assembly, causing it to rotate on its bearing. We also want to track the position of this motor, so I'll use another coupler connected to its own potentiometer. I hope this is all making sense so far. Okay, great. Using these potentiometers is what lets us know the position of the motors, and that should let us know the position of the pen. I'll attach the scissor mechanism from before, and now we see the arm can extend as well as rotate, allowing the end of the arm to reach any point in its range. And now a quick word from this video's sponsor, JLC. For this project, I need a bunch of mechatronics parts. Luckily, JLC offered to sponsor this video, and they can be a big help. Look at this list of parts I need for this project. Do you notice anything? It's long. Hunting down each of these by searching different vendors takes forever. But JLC has a catalog of mechatronics parts all in one place. That turns this list of dozens of things into really just 2. First, there's the custom structural stuff. This stuff doesn't move, nor does it need power. This is the stuff that I can just 3D print. Then there's basically everything else. All of the mechatronics parts reduced to a one-stop shop where I can get what I need from JLCMC in one go. I was able to order all of the parts I need, including these bearings, all of the gears for the gear train, and everything else to hold it all together. So, a big thank you to JLC for sponsoring this video. You may not have heard of this next one. It's mostly used in engines, but I need it for something else. Obviously, this device needs to be holding a pen, and the pen needs to sometimes be engaged and sometimes disengaged.
Aww.
In order to control this, I'm thinking we can use a cam follower mechanism. We can imagine this rod as a pen. If we can control the position of the rotating cam, we can control if the pen is pushed down against the paper or retracted away from it. So, let's print some parts. The piece rolling along the rotating cam is called the follower. It needs to have very little friction, so I'll use a small bearing. To see everything better, I'll demonstrate on this large marker. I can pop the marker into this tube with a spring. Just like a click pen, when I push down, the tip of the marker peeks out, and when I release, it retracts. But I don't want to push it by hand, I want it to be automatic. So I can use this servo, which is a small motor that can be programmed to rotate to a specific angle. Now by programming the servo to hold a specific angle, we can control whether the pen, or in this case marker, is extended or retracted. I can install this onto the end of the arm, and I can draw and write freely. By moving the motors like I'm doing here by hand, we can control the position of the pen. And hopefully I can get the robot to write better than that. All aboard the gear train. We saw gears earlier to transfer motion, here we can combine them to increase torque. I've got these motors powered up, and I'm getting pretty good motion on the rotation. The other motor controls the extension, but as is, the motor can't handle it. This is because this mechanism is currently at an insane mechanical disadvantage. The long lever arms compound the amount of torque our motor needs to produce. So we need to get more torque out of our motor with an additional mechanism called a gear train. Gears allow us to trade speed, which we have plenty of, for torque. Setting a small gear onto a large gear makes the large gear rotate slower, but with higher torque. We can couple that larger gear to another small gear, and continue daisy chaining these until we get our desired result. The first 16-tooth gear goes directly on the motor output. This meshes with a 32-tooth gear, increasing the torque by 2 times. That gear is paired with another 16-tooth gear, which meshes with a 32-tooth output on the first scissor link. That's a total of 4 times increase in torque. Now the motor has no trouble actuating the scissor mechanism. I've programmed the device to draw the reverse of whatever I draw, so I'll trace this triangle and see how it does. Well, that was completely terrible. And there's 4 major reasons. First, look what happens when I have it just draw a line. It doesn't contract or extend the whole way, it stops short. This is because there's a ton of backlash in this gear train. Look how much the scissor linkage moves before the white gear moves. This should tighten up when the metal gears arrive, but there's something else we can do that'll help a lot. See, we're currently measuring the position of our motors to determine the current position of the pen. That is to say, we're measuring the system input and hoping there's a perfect translation into our output. That's obviously not realistic. So let's try to measure the output directly instead. For example, the first motor is rotating the whole second motor assembly. So I'll measure the rotation of the second motor assembly directly. The second motor is changing the angle of the scissor linkage, so I'll go ahead and measure that directly as well. Now, even if there's slop, it doesn't matter, since the motors will continue moving until the output is correct. Now that is a whole lot better. Okay, second problem is that the motion of the first motor is less precise than the second motor. I can change the gear ratio so that a big rotation of the motor leads to a small rotation of the arm, giving more control. This is now way smoother and more accurate, but not quite perfect. The third problem is the software, so I threw some better math at this bad boy and tested each axis separately to get as detailed a measurement as possible. That means I first just rotated the arm and had it draw the curve back. If we look closely, we see a really clean result. I did the same for the extension axis, having the device just draw a straight line without any rotation, and the result is just as clean as the other motor. So the device is very successfully retracing the last thing I drew. Now it's time to move on to the last step. How are we actually going to undo something drawn in pen? Pens are permanent. You've surely seen invisible inks that write clear, but then reveal their message when heat is applied. What we need is the opposite, a special ink that writes normally, but then becomes invisible. We need some next level tech. We need Japan. These pens were invented in Tokyo in 2006. They use a special ink that turns invisible with friction. Now, I can't realistically have my device push down with the force necessary to erase, nor would that be very interesting. At this point, we all know about erasable pens. The key is in the chemistry of the ink and why friction actually erases it. The chemical structure of the ink changes with heat, and the friction of the rubber against the paper generates enough heat to trigger this reaction. So in order to erase the ink, which is central to the point of this entire project, I need to be able to generate heat. Not having enough heat is a hilarious problem to have in electrical engineering, since it usually feels like 90% of electronics is trying not to accidentally melt components. So generating heat should be no problem. I'll make a path of copper so long and so thin that its internal resistance is as high as that resistor, and in order to have it fit on the tip of a pen, I'll have to pack it into this crazy maze pattern. When I hook up voltage, it immediately gets hot, but since there's negligible thermal mass, it cools down as soon as I turn off the power. Let's install this onto the pen tip, and with that, we should have everything we need for this device to work. Alright, here we go. Oh boy. Okay, look at this.
Here we go. Pen across the whole page.
And now we hit undo. Oh my god. Oh my god, let's go. Let's go. Go. Yes. Yes. Finally. Let's go. Look at this. Look at this.
Like it was never even there. Just completely undone. There we go. Control Z, baby. Undo.
Okay, so that actually worked really well. Let's take a closer look. When I hit undo, the heater activates. The inkwell is retracted, and the pen is traced backwards along my last stroke. When the heater makes contact with the ink, it's effectively erased, leaving behind a clean paper. If I isolate just the heater, we can see the erasing more clearly. When I move the pen, this moves the potentiometers, and the device knows that I've started drawing. It records the position 30 times per second so that it has a detailed path of the line that it needs to undo. So whatever I draw, this machine can measure it, and if need be, it can undo it. So if I'm working on a drawing, and make an unfortunate mistake, I can just hit undo and redraw it correctly. That's all for today's video. Thanks so much for watching. If you like this kind of content, be sure to subscribe, and I'll see you next time.